with the Circuit Hadron video podcast. Sorry it was gone so long. I was on a vacation. So, yep. It's going to be this way all summer. Okay, so this article is this article here is on quarks. This video is going to be sort of on quarks and lots of stuff to do with sort of a quark party, I guess, if you want it to be like that. So, what is a quark? It's a elementary particle, meaning there is no known internal structure. So it's a point-like object. It has no... Yeah, it's like a point. It's a fermion, meaning it has a half-integer spin. And you can check out my fermion and boson video for more information on that. But anyway... There are 6 types of quarks: the up, down, charm, strange, and top and bottom. They can be grouped into pairs, the up and the down being one pair, the charm and the strange being another pair, and the top and the bottom being another pair. These are the 3 generations. The up-down pair is the first generation, the charm-strange pair is the second generation, and the top-bottom pair is the third generation. The only quarks found in the matter that makes up the Earth, so everything that you see right now, is solely made of up and down quarks. The charm, strange, top and bottom quarks are too unstable to be found in normal matter, but there are still composite particles like pions, kaons, mesons that are made of different types of quarks. No composite particles, however, are made of the top quark because it's too unstable. So anyway, let's get into a bit more into detail into the quarks. All 6 quarks are found in the Standard Model. All the quarks have their corresponding anti-quarks. So there's the anti-up, anti-down, anti-charm, anti-strange, anti-top, and anti-bottom, and they differ by just having their charge flipped around. So, yeah. So, getting more detail into the up quark is stable, has a mass, a nominal mass, rest mass. You can check out mass energy equivalence if you want a bit more detail on that. My video on that. Of 2.4 mega electron volts. Its charge is 2/3. It has a 1/2 spin. The down quark has a 4.8 mega electron volt rest mass. Minus 1/3 charge, again a 1/2 spin. All the quarks have a 1/2 spin, making them all fermions. And in a proton, you have 2 up quarks and 1 down quark, as you can see here. This is a proton. It's held together by virtual gluons, meaning that normally gluons don't have any mass, but virtual gluons have mass, thus they have limited range. That range being very close, so they're virtual gluons that hold this proton together. So, since the proton we know has a charge of 1, it has 2 up quarks and 1 down quark, meaning 2/3 and 2/3 is 4/3, and then since the down quark has a minus 1/3 charge, that brings 4/3 down to 3/3, which is 1. So that's how it gets its charge, the proton. The neutron has no charge, which has 2 down quarks and 1 up quark. 2 down quarks is minus 2/3, plus 2/3 from the up quark, gives it a 0 charge. So again, the charm quark also has a 2/3 charge. The strange quark has a minus 1/3 charge. So you can see where this is going, is that these are the up-like quarks, I guess they're called. They all have a charge of 2/3. The down-like quarks all have a charge of 1/3. So as well as being grouped into their 3 generations, they're also grouped into the up-like quarks and the down-like quarks, which groups them with their charges. All the quarks are subject to the weak interaction, so they can transform into a different flavor of quark, seen here in beta decay. This neutron decays into a proton by having this down quark, decay into an up quark by emitting a W boson, an anti-electron neutrino, and an electron. So, the up-type quarks, what I was talking about up here, are these, and the down-type quarks are these, just for reference. Yeah, so that's that. So, Here we go. Okay, so the up-type quarks like to change into the down-type quarks, and the down-type quarks like to change into the up-type quarks through beta decay. So down here we have the table of properties for all the quarks, and you can see they're grouped into the three generations. Their mass, the top quark being the most massive, it weighs 172 giga-electron volts. It's as massive as a gold atom, if not more, I think, slightly more. It's huge. It's extremely unstable, though. It's too unstable to be found in any mesons or baryons or hadrons, even. So that's that. The top quark was the last quark to be discovered. It was predicted by the Standard Model of particle physics. So now, those are the kind of quarks. That's pretty much the basics on them. They are subject to the strong interaction, the weak interaction. So yeah, those are the and also the electromagnetic force and gravitation. So they participate in all of the four forces. So yeah, keep in mind that the only time you can observe quarks that aren't up or down are the only quarks that you can observe in normal life, in your normal life. The charm, strange, top and bottom are too unstable to be found. They can only be found in cosmic rays and high-energy particle collisions, like in the Large Hadron Collider. And then they rapidly decay into the up and down quarks through the weak force. So, now we're going to get into some of the composite particles that make up quarks. You have baryons, which consist of all the particles that make up quarks are hadrons. That's what a hadron is, a particle made of quarks. The quarks are always held together through virtual gluons. So that's something they all have. You have baryons, which consist of 3 quarks, and mesons, which consist of a quark and an antiquark. So let's see if we can get to a page of a... Let's do a meson first. Let's see if we can get the J-Fly meson. One sec, I'll pause the video. Okay, so here we are at the meson page, and we can go look for some mesons here that are produced. Okay, so, well, anyway, we can get into a little bit about mesons. Mesons have a quark and an antiquark. All mesons are very unstable. They don't live very long at all because the quark and the antiquark annihilate to produce usually an electron neutrino, or a neutrino and a electron-like particle. That is for the charged mesons. The uncharged will usually decay into photons. Mesons really only appear in high-energy particle collisions and cosmic rays because they're too unstable to last very long. So, each meson has an antimeson where their quarks are replaced by the corresponding antiquarks and the regular quarks. So if we had a meson of an up quark and an anti-charm quark, the anti-meson would be an anti-up quark and a charm quark. Okay, so here is a table of mesons, and as you can see, the something you will notice is right here, with where the quark, the meson with its corresponding antiquark, doesn't exist. That's because they will annihilate instantly, pretty much. So those mesons won't even have enough of a lifetime to be considered a particle. The rest will annihilate a bit slower and give you some time to actually observe the particle. Okay, sorry, I had to go do something, so I don't really remember where I was. But I think I was here with the down... Actually, no, I was past that. So let's pick a meson. We'll take the neutral kaon. I think this one has a charm quark, if memory serves me correctly, in it. But, strange quark. Okay. Well, memory does not serve me correct. Kaons contain a strange quark and an up or down quark. And by strange quark, I mean a strange quark or an antiquark, and an up-down quark or an antiquark. So, kaons, I think, were the first place where they discovered strangeness. which it just means they contain a strange quark. They're very short-lived kaons. Let's see if it tells us mean lifetime. Okay, 1 point that to times 10 to the minus 8th seconds, which is yeah, very short. So that's the for the charged kaon. The neutral kaon will decay. Well, its rest mass is 497.614 mega electron volts over c squared. I have a video on electron volts. Let's go check this out. No defined lifetime. Apparently there's no defined lifetime for a neutral kaon. Interesting. Guess that's something we still have to discover, or something that is just one of those weird things where it can't possibly have a lifetime, or it's just lifetimes all over the place. But anyway, so that's a kaon. So I hope you understand mesons pretty well. Mesons have there's one more thing. They have a spin of an integer spin, making them bosons. And I think virtual pions transmit the strong force between protons and neutrons in atoms and particles like that. So virtual particles, the virtual pions transmit the strong force between protons and neutrons in atoms because they're bosons. And I think a couple of real actual particles, not pions, but real actual other mesons, will transmit the strong force also between protons and neutrons. Anyway, here's a meson with a top quark in it. These mesons are extremely unstable, and because you really don't exist, as it say, T mesons are not expected to be found in nature. Because the top quark is just so unstable. In fact, let's go to the top quark page. This is a really cool quark, because it's not standard, very unstable. Let's see, go back from the meson page to the quark page, and let's get into a little bit about this top quark. Here we go. Oops, I did not want to go to the color charge page. Quarks also carry a color charge, which which helps the strong force. Anyway, for the this is annoying me. Okay, top quark. Finally, okay. So the top quark it's a quark. So let's get into its lifetime. It has a 172.0 giga electron volt over c squared mass, which very large. It has a ton of mass to it. It usually decays into a bottom quark, and it was the last quark to be observed. Let's see if we can find its lifetime somewhere. It's very unstable. It has a very small lifetime. Properties. I'll get back in 1 sec. Okay, so the top quark's mean lifetime is predicted to be roughly 5 times 10 to the minus 25th seconds, which is too short for it to form the strong interaction through virtual gluons to hadronize, meaning to turn into a hadron. So the top quark is the only quark that they can observe outside of hadrons. In fact, at Fermilab in the CDF and D0 experiments, they actually did observe the single top quark, which is the only time they've observed a quark outside of a hadron, because top quarks can't hadronize. All other quarks will hadronize before they get a chance to study it outside of the hadron. So because the top quark is so massive, they can make predictions of the Higgs boson, which is I did a video on that, but the Higgs boson is predicted to have a similar mass. So they can, since they have such similar masses, they can predict how they will how the Higgs boson will behave to a bit. Top quark is as massive as an atom of tungsten. It's huge. This thing is a massive quark. So it's really cool. And it was predicted along with the bottom quark before it was observed. And it is part of the standard model, as we've seen before. So now we can get into the other type of hadron, which quarks make up. that have been observed. There's theories about pentaquarks and other kinds of hadrons, but those are baryons, and I'm sure they got to be somewhere down here. Okay, so here we are at the baryon page, and baryons are made up of 3 quarks, and unlike mesons, the quarks are all regular or all anti. So the anti-baryon is composed of the of the normal baryon is composed of the anti-quarks of the normal baryon. So, for example, protons and neutrons are baryons because they contain 3 quarks. So an antiproton has 2 anti-up and 1 anti-down. So that's the anti-baryon. They are fermions. So that means they interact via the strong force, unlike leptons, which don't. And so they have, yeah. Again, there's no baryons with top quarks because the top quark is too unstable. But the only stable baryons are the proton and neutron, which are made up of up and down quarks. But other kinds can be made, such as with strange, bottom, and charm quarks. But then those decay to up and down quark baryons. Okay, so here we are at the list of baryons, and here we have the proton and the neutron, which are composed of only up and down. There's also the neutral lambda baryon, which has an up, down, and a strange. It has a rest mass of 1.15 GeV, or giga-electron-volts over c squared. Has a strange value of -1, meaning it has 1 strange quark, and its mean life is 2.631 times 10 to the -10th seconds, so it has a pretty short lifetime in normal time, but for particle physics, that is a really long time to observe these particles because the detectors can work really fast. It usually decays into a proton. Okay, so here's one interesting thing. A proton is stable. So it's stable, as you would expect, because it makes up normal matter. You wouldn't expect it to decay into anything. The neutron, on the other hand, has a 8.857 times 10 to the 2 lifetime, meaning it does decay. And I think it's in about 15 minutes it usually decays, but somebody do the math for this to find out. But yeah, it decays into a proton, so neutrons actually, inside atom, or inside baryons, they are stable, but outside they do decay. So, as you can see, there's all these baryons made up of different things, and as you can see, there are again none made of the top because it is too unstable. But they do have bottom. The lowest, I guess the smallest mean lifetime for one of them is this one, the charm sigma, the up charm, has a 2.95 times 10 to the -22 seconds. All of these right here. This charm sigma right here, the up-down charm, is the most unstable one, but I'm sure anything with the top would be, well, actually that's too unstable. The rest of this is unknown, so if you guys happen to own particle accelerators, you know, pick that up and you could get some scientific credit. Anyway, so that's a baryon, and those are made of quarks, so yeah, that's it. I hope you enjoyed the video and learned something about quarks.